The Bohr model is great to describe hydrogen, but the Bohr model doesn't work to describe any atom that has more than one electron. So, section 7.3 describes the modern model of the atom. A scientist with the last name of Schrödinger comes along and introduces a mathematical model. This mathematical model is similar to Bohr's model in that it is quantized, but instead of orbits, there are orbitals, or three-dimensional areas where electrons are likely to be found. On page 255 of your text, you'll find figure 7.11. From Schrödinger's mathematical model, chemists created a probability map to show where you likely find electrons. That's represented right here. It becomes less likely to find an electron the further you go out. Chemists draw a defined shape, shown right here, to represent this orbital, and there's a 95% chance of finding an electron within this orbital shape. The first four types of occupied orbitals are s, p, d, and f. Let's first look at s orbitals. An s orbital is a sphere. A p orbital is shaped like a dumbbell. And d and f orbitals are even crazier. On page 256 of your text, you can see all four types of orbitals. We already talked about s orbital. It's a sphere. A p orbital is shaped like a dumbbell. A d orbital is a clover, and an f orbital is shaped like this. Do you remember the Bohr model? Well, here's the Bohr diagram right here. An electron closer to the nucleus has a lower energy and is smaller, has a smaller orbit, compared to an electron further away from the nucleus, which has a higher energy and has a larger orbit. Now let's look at the modern model of the atom. Orbitals that are closer to the nucleus have a lower energy and are smaller, compared to orbitals that are further away from the nucleus, have a higher energy, and they are larger. The first principal energy level, n equals 1, has a single s orbital. It is called a 1s because it is in the n equals 1 principal energy level. Now the second energy level, n equals 2, consists of s and p orbitals called 2s and 2p. The 2s is a sphere like the 1s, but it is just bigger. Now the 2p actually come in sets of 3. Now let's put all of this together. Let's have this penny represent the nucleus. Okay, so the first principal energy level is the first orbital outside of the nucleus, and that is a 1s. Now the nucleus is in the center of that 1s. Okay, there's my 1s. Now the second principal energy level is represented by a 2s as well as a 2p that has an x, y, and z orientation. So let's look at that. A 2s is larger than a 1s, and it encompasses that. So now inside there's the nucleus, the 1s, and then you see the 2s. Now also at the second principal energy level, n equals 2, there are 3 p orbitals. So let's put the p orbitals in here. Okay, now the p orbitals are in here. So inside there's the nucleus, then the 1s, and then the 2s, which is represented by the purple sphere, and then also the p orbitals. So there is a x orientation, a y orientation, and a z orientation coming out at you. After that, you continue to add principal energy levels to n equals 3, n equals 4, etc. So how do we keep track of all of this, and how do we know where the electrons are? Well, we say we have these orbitals at certain energies, but where are the electrons for specific atoms at ground state? Here's an orbital diagram. This is what we use to help us keep track. This is an orbital diagram for hydrogen. Sublevels in the same principal energy level have the same energy only in atoms with one electron. If there is more than one electron, the interaction between the electrons causes the sublevels within the same principal energy level to have different energies. So again, look at the principal energy level. N equals 1 has one orbital and one sublevel. The sublevel is S, and it has a 1s orbital. This box represents an orbital. At n equals 2, there are two sublevels, an s sublevel and a p sublevel. At the s sublevel, there is one orbital. At the p sublevel, there are 1, 2, 3 orbitals. At n equals 3, there are 3 sublevels. Here's an orbital diagram for a multi-electron atom. We have the 1s, and then we have the 2s. Now before, when we only had one electron example, such as a hydrogen, we had the 2s on the same line as the 2p. Because they had the same energy, because there was only one electron. Now if there's more than one electron, they interact and they cause the sublevels within the same principal energy level to have different energies. So the 2s is at a lower energy than the 2p. Now where do the electrons come into play? Electrons always fill closest to the nucleus first, and then you move up or away from the nucleus to a higher energy. So let's take an example. How about carbon? So in carbon there are 6 electrons we need to worry about. Now the way the electrons work is they will fill closest to the nucleus first, and then they will fill other orbitals. Now as they fill, there are a few rules to keep in mind. First off, there are only 2 electrons allowed in each orbital. That is called the Pauli exclusion principle. The Pauli exclusion principle states that 2 electrons are allowed in each orbital and they must have opposite spins. So let's start there. So if I have 6 electrons that I need to put in this diagram, I will start at the bottom closest to the nucleus. So I have 1 electron and a second electron. My next step is to add the electrons to the 2s sublevel, which has a 2s orbital. So there's my third and my fourth electron. Now I have 2 electrons left for a total of 6, right? So my next sublevel is the 2p sublevel. In the 2p sublevel, I have 3 orbitals. I have an orbital in the x orientation, in the y orientation, and then in the z orientation coming out at you. This brings us to this next rule called Hund's rule. Hund's rule states that electrons are distributed into orbitals of identical energy before they go back and double up. Meaning, if I have 2 electrons left, I can't put them both in this orbital. That just doesn't work. I would place them in 2 separate orbitals. A good reminder for this would be an apartment. If you go into an apartment and there are 3 rooms and there are 2 people going into the apartment, those 2 people won't go in the same room. They're going to spread out. They're going to go into 2 separate rooms. Well, this is the diagram for carbon. What's the electron configuration for carbon? Well, I know I have a 1s. And I know I have 2 electrons in my 1s sublevel and my 1s orbital. Next is my 2s sublevel, and there's 1 2s orbital in my 2s sublevel. So 2s, there are 2 electrons in that orbital. Now in my 2p sublevel, I have 3 p orbitals. So in my 2p sublevel, I have 2 electrons, and those 2 electrons are found in separate orbitals. This is the electron configuration for carbon. Here's an example problem for us. What element has the following electron configuration? Well, here's a quick trick. How many total electrons do I have? 2, 4, 9. I have 9 total electrons. Look on your periodic table and figure out what element has 9 electrons. Fluorine has 9 electrons. So the electron configuration was for fluorine.